Work, energy and power. Question 1. The diagram below shows a track ABC. The curved section AB is frictionless. The rough horizontal section BC is 8 meters long. An object of mass 10 kg is released from point A, which is 4 meters above the ground. It slides down the track and comes to rest at point C. 1.1.1. State the principle of conservation of mechanical energy in words. The principle of conservation of mechanical energy states that the total mechanical energy in an isolated system remains constant. 1.1.2. Is mechanical energy conserved as the object slides from A to C? From A to C. The answer is no. Why do we say no? We say no because mechanical energy is only conserved when there are conservative forces acting on our object. From A to B, there's only gravitational force pulling our block from A to B, right? So it is conserved. But then when you get to B all the way to C, our surface is rough, so there's frictional force, and frictional force is a non-conservative force, meaning mechanical energy is not conserved from B to C. So they asked us whether or not it is conserved from A all the way to C. So it is not conserved because BC is included. 1.1.3. Using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves along BC. Since we have stated that mechanical energy is conserved from A to B, we can use the conservation of mechanical energy equation to calculate the velocity of our object when it reaches point B. The equation looks like this. Mechanical energy of our object at the top is equal to mechanical energy of our object at the bottom, meaning from A to B. Now when we expand it, it looks like mechanical energy is when you add kinetic energy with potential energy. So it is EK plus EP at the top is equal to EK plus EP at the bottom. Furthermore expansion, it looks like this. Kinetic energy is half mv squared. Potential energy is mg height at the top is equal to half mv squared plus mgh. Now the mass of our object is 10 kilograms and the height at the top is 4 meters, so 10 kilograms. Now the velocity of our object at point A is 0 because our object is still stationary. 0 squared plus 10 into 9,8, the gravitational acceleration. What is the height at the top of the track? It is 4 meters above the ground. Half mass is 10 kilograms. Now the velocity of our object at B, that's what we're looking for. So we have v squared plus 10 into 9,8. What is the height at point B? It is 0 meters above the ground. So this is going to give us 0, and this is going to give us 10 times 9,8 into 4. 392 is equal to, now half times 10 is 5 v squared. This is going to give us 0, right? 392 is equal to 5 v squared. We're going to divide by 5, divide by 5. This 5 is going to cancel with this one, and we'll be left with v squared. Now in order for us to get rid of the squared, we will have to put this whole thing inside of a square root. 392 divided by 5. Now the velocity of our object at point B is equal to 8,8 0.85 meters per second. So the velocity of our object at point B is 8.85 meters per second, right? And we are told that when our object reaches point C, it stops, meaning the velocity at C is 0 meters per second. So this is our V initial and this is our V final. And we are also told that from B to C, our track is 8 meters long. So our delta X is 8 meters. So from this information, we can tell that we are going to have to use one of the equations of motion to calculate the acceleration of our object. The equation which we're going to use is this one. V final squared is equal to V initial squared plus 2a delta x. 0 squared is equal to 8.85 squared plus 2a into 8. Now this squared is going to give us a number and we're going to move it to this side, so it's going to be negative 8.85, negative 78.3225 is equal to 8 times 2 is 16a. Divide by 16, divide by 16. Our acceleration is equal to negative 4.89516 meters per second. Now our acceleration is negative because our object is slowing down. From B to C, our object is slowing down. Now since we have the mass of our object, which is 4 kilograms, and we have the acceleration, we can use Newton's second law of motion to calculate the frictional force, because friction is the only force acting on our object when it moves across this section. Frictional force is equal to ma. Now the mass of our object is 10 kilograms and the acceleration is negative 4.89516. We don't round off until we get to the final answer, guys, so don't make that mistake of rounding off before you get to the final answer. Frictional force is equal to 48.95 newtons to the left. 1.2. A motor pulls a crate of mass 300 kilograms with a constant force by means of a light inextensible rope running over a light frictionless pulley as shown below. The coefficient of kinetic friction between the crate and the surface of the plane is 0.19. 1.1.2. Calculate the magnitude of the frictional force acting between the crate and the surface of the inclined plane. Now the first thing that we need to do is to draw a free body diagram of our object. Normal force, weight, force of the motor, and there's frictional force. Now when you break down the components of the weight, we'll get weight perpendicular and weight parallel. Now you can clearly see that normal force is equal to weight perpendicular. Normal force is equal to weight perpendicular. So in order for us to calculate the frictional force, we're going to multiply the coefficient of kinetic friction with our normal force. But then we know that our normal force is equal to weight perpendicular, right? So they told us that it is 0.19 times weight perpendicular is mg cos theta. 0.9 into our mass. The mass of our object is 300 kilograms times 9.8 cos of 25 degrees. 25 degrees. 0.19 into 300 times 9.8 cos of 25. 506.26 newtons down the incline. Now before we get to 1.2.2, they tell us that the crate moves up the incline at a constant speed of 0.5 meters per second. 1.2.2, calculate the average power delivered by the motor while pulling the crate up the incline. The formula that I want you to think about is this one. Average power is equal to force times average velocity. Power is equal to the force causing our object to move, which is the force of the motor, times the average velocity of our object. So we are going to have to find the value of this force. And in order for us to do that, we already know the frictional force. We're going to use Newton's second law. F net is equal to ma. Now up the incline is positive. And then they told us that the crate moves up the incline at a constant speed, meaning there is no acceleration. If there's no acceleration, then this is going to give us 0. F net is equal to 0. Now what are the forces acting on our object? We have force of the motor going up the incline, so it's going to be positive, and we have friction and weight parallel going down the incline, so they're going to be negative. Force of the motor minus frictional force minus weight parallel is equal to 0. I'm going to move them to this side, so they're going to be positive. Fk plus W parallel. Force of the motor is equal to Fk plus, this is mg sine theta, right? Now what is our frictional force? It is 506.26 newtons plus the mass of our object is 300 kilograms. 9.8 sine of, what is our angle? 25 degrees. Now when we plug that into our calculator, we get 1748.76 newtons. Because this is our final answer, we need to round it off to 2 decimal places. Up the incline. Now we haven't answered the question yet. In this equation, we now know the force of the motor and the average velocity. So power average is equal to this force, 1748.76 into 0.5 meters per second. 0.5 meters per second. We get answer into 0.5, 874.38 watts. That's our final answer. Thank you for watching.